In 1859, Victorian telegraph operators they were suddenly dodging sparks as their machines literally caught fire.
Yeah, just bursting into flames right on their desks.
Right. And some of them realized they could just completely disconnect their power batteries, and their telegraphs kept right on sending messages. They were being powered by this massive, invisible force from the sky.
Which is pretty wild to think about.
It's insane. And today, that exact same invisible force is aimed directly at the bottom of the Atlantic Ocean, and our modern world is just, sitting right in its path.
The contrast there between those sparking telegraph machines and our current, hyper-connected infrastructure is really sobering. I mean, when we think of catastrophic threats, we tend to look down here on Earth, right?
Oh, absolutely. We worry about cyber attacks or physical grid failure.
Right, physical sabotage, stuff like that.
Yeah.
We rarely look up at the star that actually sustains us, which, astronomically speaking, is mathematically guaranteed to unleash that exact kind of chaos again.
Welcome to this deep dive. Today, we are exploring a very real, scientifically proven threat, which is a massive solar superstorm. Our mission here is to unpack a stark space science report detailing NASA's latest warnings about unprecedented solar activity.
Yeah, it's not looking great.
No, it's not. We really need to understand exactly why our highly advanced digital civilization is floating essentially unprotected in the path of a cosmic tsunami.
And just to clarify, we aren't talking about a Hollywood disaster movie where the Earth physically melts.
Right, no Bruce Willis flying up to an asteroid here. We are talking about the sudden, silent death of the global internet and the power grids we rely on to survive. Okay, let's unpack this. So NASA is tracking some intense volatility on the sun right now, and it's pointing to a period called the solar maximum.
Yes, exactly.
And I saw in the notes that this volatility operates on a strict 11-year cycle. How exactly does a rhythmic cycle on the sun translate into an apocalyptic threat down here on Earth?
Well, the trigger is really the fluid mechanics of the sun itself, because the sun is just this churning sphere of electrically charged hot gas.
Like plasma.
Right, plasma. It doesn't rotate uniformly like a solid planet does. So the equator of the sun actually spins much faster than its poles.
Oh, interesting. So it's kind of twisting itself.
Exactly. Over the course of an 11-year cycle, this differential rotation drags the sun's internal magnetic field lines. It's twisting and stretching them tighter and tighter.
Until they get wound up so much that the magnetic tension just becomes completely unsustainable.
You got it. And when those heavily tangled magnetic field lines finally snap and just forcefully realign, that violent release of stored energy, that is the solar maximum.
And we are in a highly active phase of that right now.
We are. And that snap is what launches the actual projectile in this scenario, which is a coronal mass ejection, or a CME. Now, we all know what a basic solar flare is, right?
Sure, like a burst of electromagnetic radiation, mostly just light that hits Earth in about 8 minutes.
Right. But a CME is a completely different beast.
Because it actually has mass. We are talking about billions of tons of magnetized plasma, like actual physical matter, tearing through space at millions of miles per hour.
Yeah, a giant cloud of charged particles. And because it's physical matter, it takes time to cross the 93 million miles to Earth.
So we'd see it coming.
Yeah, we might have a day, maybe 3 days of warning if we see it coming. But the visual of a CME hitting Earth is often really misunderstood. I mean, it's not a wave of fire that torches the atmosphere.
Right. If you picture a wall of fire, you're missing the mechanism of destruction entirely. Let's try to visualize this for a second. Instead of a fireball, imagine Earth's magnetic field as a giant, taut guitar string stretching out into space.
That's a great way to look at it.
The CME is like a massive invisible hand that reaches out and violently plucks that string. When that bubble of magnetic energy and plasma slams into our protective shield, it doesn't burn us. It causes our planet's entire magnetic field to vibrate wildly. So if this cosmic tsunami doesn't physically burn us, how does a magnetic bubble actually break our physical stuff down here on Earth?
What's fascinating here is the underlying physics of that vibration, which is governed by Faraday's law of induction. Basically, a fluctuating magnetic field induces an electrical current in any conductor present within that field.
So like moving a magnet near a wire forces electrons to move through that wire.
Yes, exactly. But on a planetary scale, Earth's vibrating magnetic field essentially turns the entire planet into a massive electrical dynamo.
Wow.
The fluctuation induces these enormous, uncontrolled direct currents in the crust of the Earth itself.
But we don't notice it. Like, human bodies aren't long conductive wires, so we are entirely oblivious to it. We wouldn't feel a thing.
Right, we wouldn't feel it at all. But any exceptionally long piece of metal stretched across the Earth's surface suddenly becomes an unwilling participant in this massive electrical circuit.
So the longer the wire, the more current it absorbs from the fluctuating magnetic field.
Exactly.
We're talking high voltage power grids, vast pipeline networks, telecommunication lines. They just soak up these geomagnetically induced currents until the hardware attached to them physically burns out.
Yeah, the hardware simply isn't designed to handle massive influxes of direct current injected straight from the ground. Like transformers in our power grid, for instance, they're designed for alternating current.
Okay, so the direct current messes them up.
Completely. When you force massive amounts of direct current through them via their grounding wires, their magnetic cores saturate. They just overheat, the copper windings melt, and the transformer violently fails.
And replacing a custom-built, multi-ton, high-voltage transformer, I mean, that can take months under normal logistical conditions.
Years sometimes, yeah.
So if Faraday's law turns the longest continuous metal structures on Earth into the biggest targets, my mind immediately goes to the absolute longest wires we have, which are the undersea cables. I mean, the global internet doesn't live in the cloud, it lives at the bottom of the ocean.
Right. Thousands of miles of cables draped across the Atlantic and Pacific seafloors, handling about 99% of all transoceanic digital communication.
It's basically everything.
It is. Financial markets, military communications, basic internet routing protocols, all of it flows through those physical lines.
I read through the sources on this, and there is a brilliant, almost terrifying irony to how this technology is built. The cables themselves use fiber optics. They transmit data by bouncing photons down hair-thin glass tubes.
Right, glass.
And since glass isn't a conductor and photons don't care about magnetic fields, the data streams themselves should theoretically be completely immune to a geomagnetic storm.
In theory, yes, the glass fiber is totally immune. But, well, light obeys the laws of physics, specifically attenuation. Even in the purest glass ever manufactured, a light signal degrades as it travels.
It's like it just gets dimmer.
Exactly. You cannot fire a laser from New York and have it arise in London with enough intensity to be read by a receiver. The signal scatters and fades. So, to prevent the data from disappearing into darkness, engineers install electronic devices called repeaters at intervals of roughly 30 to 50 miles along the entire length of the transoceanic cable.
Wait, so the miles of actual cable are fine because they just use light, but the little chargers along the way get fried by ocean floor electricity?
Yes. They are basically little underwater amplifiers that catch the fading light, convert it, boost it back up to full strength, and shoot it down the next segment of glass.
Okay, so they need power.
Exactly. If we connect this to the bigger picture, those repeaters represent the ultimate single point of failure for the modern world. They are electronic devices, meaning they require a constant, reliable supply of electrical power to function. You can't just plug them into a wall socket on the ocean floor.
Right, obviously. So they have to send the power from the shore.
Yep. The power has to be sent from the shore stations alongside the data. So wrapped around those delicate immune glass fibers is a thick, highly conductive copper sheath running the entire length of the ocean.
The longest continuous conductor on the planet sitting in salt water. And salt water is practically the perfect electrical conduit.
Seawater is an excellent conductor, so when the CME hits and induces those massive currents in the Earth's crust, the ocean floor becomes highly charged. The voltage potential between different landmasses shifts wildly.
And electricity always takes the easiest route.
Right, the induced direct current seeks the path of least resistance. Instead of traveling through the resistive rock of the seabed, the current leaps into the highly conductive seawater and then surges straight into the copper sheathing of our internet cables.
It just hijacks the power line meant for the repeaters.
It floods the line with thousands of volts of wild, unconditioned direct current. The repeaters are designed with basic voltage regulators, sure, but they are absolutely not engineered to withstand a direct hit from a planetary-scale geomagnetic surge.
Or say just fry.
The internal electronics overload, overheat, and short out instantly.
And the second those repeaters die, the light signal hitting them stops dead. The physical fiber optic glass might be perfectly intact from New York to London, but without the repeaters boosting the signal every 40 miles, the data simply degrades into nothingness halfway across the Atlantic.
That's it. The transatlantic link is severed. Not just one cable, but potentially all of them, simultaneously.
The cascading failure of the global internet routing protocols like BGP would be instantaneous. Routers would desperately try to find alternative paths for the data, but with the massive trunk line severed, the remaining terrestrial networks would be instantaneously overwhelmed by the traffic.
The entire system gridlocks. It is a complete collapse of the global digital infrastructure.
This isn't just an inconvenience where you can't load a streaming service. We are talking about the freezing of international banking. Trillions of dollars in automated transactions vanish into a void. Supply chain logistics, which rely entirely on digital tracking for just-in-time delivery, they grind to an absolute halt.
Cargo ships wouldn't know where to dock. Trucks wouldn't know what to carry.
And replacing these repeaters is a monumental physical challenge. You can't just send a guy in a van to swap them out.
No, not at all. To fix a broken repeater, you need a highly specialized cable-laying ship. The ship has to sail out to the exact GPS coordinates in the middle of the ocean, lower a grapple thousands of feet to the abyssal plain, hook the cable, and haul it up to the deck.
Thousands of feet down.
Yeah, and then engineers have to physically cut the cable, splice in a brand new repeater, seal it against the crushing pressure of the deep ocean, and lower it back down.
And they would have to do that for thousands of blown repeaters all over the planet, all at the same time, while navigating a world that has no GPS, no internet, and widespread power grid failures on land.
It would take months, perhaps years, to manufacture enough replacement repeaters and physically deploy the handful of specialized ships required to fix the network. The digital blackout wouldn't just be a temporary outage. It would be an era.
The terrifying part of diving into these sources is realizing this isn't a theoretical physics exercise. This isn't a hypothetical what if, it's a when it happens again. The historical precedent is staring us right in the face, and it happened relatively recently in human history.
Right, September of 1859, the Carrington Event. It remains the benchmark for extreme space weather. And the sequence of events back then perfectly illustrates the mechanics we've just discussed, albeit on a much more primitive technological stage.
Here's where it gets really interesting. So Richard Carrington, a British astronomer, was sketching sunspots in his observatory. He was projecting the image of the sun through his telescope onto a screen. And suddenly, two patches of intensely bright white light erupted from the sunspot group.
He was literally watching the magnetic field lines snap in real time.
He witnessed the solar flare, the initial flash of light that arrived 8 minutes after the eruption.
But what he couldn't see was the massive coronal mass ejection, the cloud of plasma that was launched directly at Earth. Given the incredible speed of that particular CME, it crossed the 93 million miles in just over 17 hours.
Which is insanely fast. The sources describe the impact as surreal. The aurora borealis, the northern lights, which are caused by solar particles interacting with our upper atmosphere and usually stay near the poles, they were pushed so aggressively toward the equator that they were seen in Colombia.
All the way down near the equator?
Yes. People in the northeastern U.S. woke up at midnight, saw the sky glowing red and green so brightly they thought their cities were on fire, and they literally sat outside reading the newspaper by the light of the aurora.
The visual spectacle was awe-inspiring, I'm sure, but the physical effects on the ground were exactly what Faraday's law predicts. In 1859, the longest continuous conductors on Earth were telegraph wires, the Victorian Internet.
Thousands of miles of copper wire strung up on wooden poles across North America and Europe.
The perfect antennas for geomagnetically induced currents. Telegraph operators were the first to feel the brunt of the storm.
Right, they were getting shocked.
Yeah, as the Earth's magnetic field vibrated, massive voltages were induced into the telegraph lines. Operators reported receiving severe electrical shocks just from touching their telegraph keys. The currents were so intense that sparks were leaping off the equipment, literally setting the paper ticker tape on fire in the offices.
And my absolute favorite detail from the source material. Operators in Boston and Portland realized the induced current in the wires was so strong and steady that they unplugged their massive chemical batteries.
They just bypassed their own power entirely.
They completely disconnected the power source, and they were still able to tap out messages to each other for hours, powered entirely by the auroral current flowing down from the atmosphere. They were communicating via solar storm.
It is a remarkable historical anecdote. But, it also highlights the crux of our modern vulnerability. In 1859, the telegraph catching fire was a startling anomaly. It delayed some messages and caused a few localized fires in telegraph offices. But society didn't collapse.
No, the average person walking down the street in London or New York in 1859 barely noticed anything other than the pretty lights in the sky. Their heating came from coal or wood. Their food was grown locally or transported by steam and horse.
Exactly.
They didn't rely on synchronized power grids or global data networks to keep the water pumping and the hospitals running.
This raises an important question regarding the fundamental trajectory of our technological progress. We tend to view our advancements, the internet, global supply chains, automated grids, as systems that make us more resilient.
But they don't, do they?
In reality, every layer of electronic complexity we add to our civilization inadvertently increases our exposure to this specific cosmic threat. We have spent the last century and a half building an incredibly intricate, highly fragile house of cards, perfectly tuned to be knocked over by a geomagnetic storm.
If that exact same 1859 Carrington Event storm were to hit us tomorrow, it wouldn't just be a few spark telegraphs. The sources estimate the economic impact in the trillions of dollars, but even trillions of dollars feels like an abstract number that fails to capture the visceral reality of the damage.
It's hard for the human brain to even process that scale.
We're talking about the physical destruction of the high-voltage transformers that form the backbone of the power grid and the simultaneous frying of the undersea repeaters that hold the internet together.
We are looking at the cascading failure of modern logistics. Modern cities are essentially deserts of concrete that require a continuous massive influx of food, water, and fuel just to survive.
Yeah, supermarkets operate on just-in-time delivery models, keeping only a few days of inventory on hand.
And those deliveries are coordinated entirely by algorithms communicating over the internet. When the undersea cables fail and the terrestrial networks gridlock, those trucks stop moving. Water purification plants, which rely on industrial control systems and constant electricity, just cease operations.
The source material uses a metaphor that I just haven't been able to stop thinking about. We are floating on a fragile technological raft in a violent cosmic ocean, completely at the mercy of our star.
It's a very apt way to put it.
We've spent decades making this raft larger, heavier, and more complicated, just assuming that the ocean beneath us will remain calm forever. But the strict 11-year cycle of the solar maximum proves that the ocean does not stay calm.
It really doesn't.
Yeah.
The plasma bubble of a coronal mass ejection doesn't recognize our firewalls, our encryption, or our cybersecurity protocol.
It doesn't care about our software.
It bypasses our software entirely and exploits the fundamental physical laws of electromagnetism to destroy the hardware from the inside out. The threat is concrete, it is historically proven, and it requires a massive paradigm shift in how we build infrastructure. We have prioritized efficiency and speed over resilience and redundancy.
So what does this all mean? We started this deep dive looking at a stark warning from NASA about the current solar maximum, and we've unpacked a reality that completely shifts how we view the technology we rely on every single day.
It really does shift your perspective.
We've looked at the fluid mechanics of the sun, understanding how tangled magnetic fields eventually snap and launch billions of tons of magnetized plasma directly at our planet.
And we explored the physics of Faraday's law, seeing how that vibrating magnetic shield turns the Earth itself into a massive electrical generator, injecting uncontrolled direct currents right into our critical infrastructure.
We dove down to the bottom of the ocean to expose the hidden Achilles heel of the modern world, the electronic repeaters attached to our undersea fiber-optic cables, just waiting to be fried by ocean floor currents, severing the continents from one another. And we looked back at the 1859 Carrington Event, realizing that our leap from steam and telegraphs to algorithms and global internet has ironically made us vastly more fragile than our Victorian ancestors.
It demands that we confront the illusion of permanence in our digital realm. Hardening our power grids and redesigning our undersea networks to withstand massive geomagnetic currents isn't just an abstract engineering challenge, it is an existential imperative for a hyper-connected civilization.
It definitely changes your perspective. The next time you're stuck at a red light or swiping your card at the grocery store or even just screaming this very deep dive, take a second to realize how reliant all of it is on a delicate balance of deep-sea cables, high-voltage transformers, and sheer cosmic luck.
It's all hanging by a thread.
And that brings me to a final thought I want to leave you, the listener, with today. We focused heavily on the breakdown of global systems, the severing of transatlantic cables, the collapse of international supply chains, but I want you to zoom in and look at your own neighborhood.
Localize it.
Right. If a Carrington-level storm hit tomorrow, blowing the transformers and wiping out global communications for years, How would your local community reorganize itself without a digital supply chain telling everyone what to do? Would humanity immediately fracture into isolated, panicked pockets fighting over the remaining resources? Or would a sudden forced disconnection from the global internet spark a massive, localized renaissance in how we collaborate, grow food, and survive together, face to
It
face?
would be the ultimate stress test of human adaptability.
It truly is. Thank you for joining us on this deep dive. Keep questioning the systems you rely on, keep looking up at the stars, and we'll catch you next time.